question. We are converting between radians and degrees. 6 pi over 7 radians. I want degrees. Bruno, how do I do that?
Just put 6 pi over 7 and multiply it by 180 divided by pi.
Very good. Unit-wise, that's going to cancel the radians, leave me with degrees to my answer. The pi's are going to cancel. And if you try and simplify that on your calculator, it gives you this for the numbers, which is not pretty. And I'm assuming most of you gave me a decimal answer. What did you get, Bruno?
I got
154.3 degrees. Can I get a thumbs up if you agree? That would be correct. Very good. And most questions involving a degree answer, it's fine to give a rounded decimal because degrees are tiny. With radians, it's important to give the actual fraction and not a rounded decimal because remember that radians are big. And so rounding means you're cutting off a huge chunk of that section of the graph. So degrees you can round. Radians, we want exact answer. I need a different volunteer for the second one. Converting from degrees to radians. Oh, frowny face. Frowny face, Alex. I want to take 125, turn it into radians. How do I do that? Do we agree? Very good. Very good. And we can reduce this to some extent because I know that 125 and 180 are both divisible by 5. Somebody with a calculator, what's 125 divided by 5? 25. What is 180 divided by 5? 36. And 25 is 5 squared, 36 is 6 squared. They have nothing in common. So now I can just multiply straight across the top. 25 pi, multiply straight across the bottom, I get 36. I see some nodding. Good. That makes sense. 125 is smaller than 180. I should get something that's a little bit smaller than pi, which is equivalent to 180. So that makes sense. Good. Good. Happy face. Questions on the unit conversions? No. Okay. You got it? Third one said make sure your calculator's in radian mode and graph y equals sine x. Do I have a volunteer who can describe what they saw? You can use your finger to show me if you want. Yes, Mirza. So it started increasing and then decreasing like this. And I am a horrible drawer, but I think that is a good representation of what we were seeing on a graph. Very good. And most of you guys had a graph that went back the other way as well and did that same shape. Very good. What do we notice about that picture? Descriptive words that describe that. What do we notice? So y int at origin. Yeah? What else? Lots to notice about that graph. What else do we notice? On your graph, you probably saw in both directions. What do you notice about that shape? It's infinite. Yeah, it keeps going and going, and it repeats. Yeah. Because I have this cycle here that started at 0, went up, and then down. And at the end of that cycle, it starts the process over again. Up and then down, and then up and then down. we're taking that red section and copy pasting it to the tail of the next section over and over again. Yeah, good. What we are going to start talking about today and what all of our next unit is about functions that behave like this, that are repeating. Repeating. Also known as periodic functions. Good. Does anybody have questions on our bell ringer? No, everybody's wide awake and perky as usual. Good. Okay. I need someone to pass out the 2C notes while I click some stuff on my calculator or computer. Volunteer. Thank you, Dave. We're going to take some notes on periodic functions. You will want either your calculator or a Chromebook because we are going to do some graphing at the end of the notes. Oh, wait, no, that is not what I wanted. I want this. Everybody has a copy in front of them? Very good. So today we are talking about periodic functions. And just as we saw with our graph of sine x, periodic functions repeat. And there is an important phrase here. They repeat at regular intervals. The question is, what does that mean? Once every cycle, once every second, once every minute, okay? We have two examples, sine and cosine. We just saw the sine graph. We know cosine's related to sine. So I expect it's going to look very similar. Those are periodic functions. How often do sine and cosine repeat? How many degrees or radians does it take me to get all the way around the unit circle? Yeah, I was about to say 1 pi is here. 2 pi would be here. Good. So 2 pi radians or 360 degrees. We're going to stick to radians from here on out. If you use degrees, your graphing calculator is going to give you very funny pictures. So we want radians from here on out. Good. So I want you to take about 2 minutes in your small group, and I want you to discuss things that repeat at regular, predictable, constant intervals. Examples in the real world of things that do that. I'll give you a hint. There is a picture of one thing up there in your notes. Take about 2 minutes and discuss. Okay. Examples. Who has an example? Frowny face. We'll just go around the room. Bruno, what was your example? Very good. So heartbeat. We could have clock. Hands on a clock. In a circle. We know circles repeat. Very good. Yeah, but that's okay. Ethan, what do you got? You had one. I think if you put both of these at rest, then yes, those should be repeating with regular interval. We need a healthy, steady flow of oxygen to our brain. Yes, Louis?
Oh, I said like the McDonald's beeping
That is true. It does repeat with regular intervals. Good. What else? Let's see. Melanie, what did your table come up with? Oh, a ruler? Oh, the major hash marks repeat. Yeah, the patterns on a ruler. Yeah. Pattern on a ruler repeats. Good. Alan, what about your table? Waves? What kind of waves? What other kind of waves, Jordan? Light waves? Somebody else had another type of wave? Sound waves? Yeah. Most of those waves you hear about in science class are periodic and are described with periodic functions. Yeah. Very good. Back row, we have any contributions that aren't already up there? Yeah, very good. Running out of space here. Pendulum ties into that idea of a clock. Those old grandfather clocks had pendulums on them. Yeah. Yes, but I'm going to write it a little bit differently than you said it. The Earth's rotation. Yeah, which is what produces the sunrise and sunset. How often do we make one complete rotation about our own axis? You're thinking Earth about sun. I'm talking about Earth about itself. One day, yeah, that's what defines a day, is one complete cycle about its axis. Yeah, so the Earth's rotation about its own axis repeats every 24 hours. The Earth's rotation about the sun repeats a little bit more than every 365 days. The solar system has a regular rotation about the center of our galaxy. So yeah, the Earth is rotating in a whole lot of different ways. And if you take physics, then you learn our galaxy is moving outward from the center of the universe at a crazy speed. So we're moving faster than the speed of sound, just standing still. Physics is fun. Good. Tons of stuff in nature. Anything that repeats. If you're driving your car and you've got cruise control on, those wheels, that's periodic motion. You're riding your bike at a constant speed, periodic motion. Anything that is repeating. Yeah? Good. The frequency, or not the frequency, the interval over which it repeats, 24 hours for one complete rotation about an axis, 365 days about the sun, is called the period of the periodic function. And the nice thing about periodic functions is that because it repeats every period, it should have the same value every period. So for sine, I start at 0, my y value is 0. If I go over to 2 pi, what is sine of 2 pi? That's a whole period. I'm back at 0 again. I'm at 4 pi, what is the value of sine? It's another period away, it should be 0. 6 pi away, it should be 0. 8 pi away, 0. Yeah, it repeats every pi. So if you know where it is, where it starts, every 2 pi is going to have that same output. Good. Another way to write that is f of x is equal to f of x plus or minus n times p, where p is the period. N is a whole number. It is. But it's a useful, complicated expression. Let's see. Alex is back. Marissa is back. Yeah. As long as I know the output at x, x plus or minus any multiple of the period is going to give me the same output as the div of x. Sine of 0 is 0, sine of 2 pi is 0, sine of 4 pi is 0, sine of 100 pi is 0, because 100 is divisible by 2. Good. There are a couple of properties that we're going to see over the next couple weeks as we learn about periodic functions. So first, we like periodic functions. They are generally symmetric. 2 ends, right? Yes. and they repeat along the horizontal axis. If they repeated it along the vertical, they wouldn't pass the vertical line test. They wouldn't be functions. So they repeat along the horizontal. The next thing is that that period is constant across the entire range of the graph, entire range of the function. The whole graph, that period should be constant. My fourth period had some examples of repeating things in nature that weren't constant, like stocks. You watch the stock markets, you tend to see that same spiky pattern over and over. But because it's driven by human behavior, which is inherently non-predictable, it doesn't repeat with constant intervals. Words are hard today. So now some weird stuff. I have a function, f of x, that I know is periodic. For example, sine x. There are a few things that I am allowed to do to that function, transformations I can do to that function, that will produce another periodic function. The first is I can take that function and look at its reciprocal. Spits out a periodic function with period p. Yeah, same period. I can do horizontal transformations, meaning I can stretch and compress sideways. I can pick up the graph and slide it sideways and produce another periodic function. So that would look like f of ax plus b. Because the transformations are inside the parentheses, they're happening on the horizontal axis, the x-axis. So A, we're grabbing the edges of the graph and stretching or compressing. B is taking the graph and sliding it side to side without changing the shape. When we do that, B doesn't affect the shape. I'm just picking it up and sliding it. So the length of a cycle doesn't change. But when I take the edges of that sine curve and I pull outward, it's now going to take me more distance to complete a whole cycle because I just took the edges of that cycle and stretched outward. A is going to change my period. So if I'm looking at horizontal transformations and it's a dilation, a stretch, my new period is going to be the period divided by the absolute value of that dilation factor. I don't expect you're going to remember that. You are going to see it with some activities we're going to do the next couple of days as you get familiar with these functions. I know, it's fifth period, we're tired. Next one, we've done horizontal transformations. We can also do vertical transformations. So I can grab the high and low points of a sine curve and pull up and down, or squish inward. I can take the whole sine curve and shift it up or shift it down. So that would be A times f of x plus b. The changes are happening outside the function. They're happening to the answer and not the input. And the question is, what do those transformations do to the period? So we're going to do a little thought experiment. So there's one cycle of a sine function, one complete cycle. A times f of x would take that peak and that valley and pull out, making them taller at every point. And the question is, does that change the length of the wave? No. 0 is still 0. because it doesn't matter what I multiply f of x by. If f of x is 0, a times f of x is going to be 0. So this multiplication doesn't change the period. If I take the whole graph and I shift it upwards, that should have been a different color. Let's try that again. Have I changed how long the wave is? No. So transformations on the answer, vertical transformations, do not affect the period at all. The period of the new function is the same as the period of the old function. So generally, when I'm playing with periodic functions, I only have to worry about horizontal transformations. Everything else, I'm going to get another periodic function with the exact same period, same behavior. Good. I have a question because I don't remember if I've asked this question. Is anybody taking or has taken like physics plus universe or some physics class here? Chemistry? A whole class full of dual enrollment pre-cal and trig students who hate science? Sad face. Well, in bio, you might see this at some point, because again, parts of living beings do this. But in science, when we talk about the period of a periodic function, instead of looking at it as sine of x, we're looking at sine of t. We're looking at things that oscillate in time. And so oftentimes you see a period as a measure of the length of time per cycle. Here it's going to be distance per cycle because we're doing x instead of t. And I know per means divide, so it's like seconds per cycle or minutes per cycle. If I'm talking about the Earth's rotation, we know it's 24 hours per cycle. If we take that and we flip it upside down, we look at its reciprocal, we get something called frequency. Frequency is 1 over the period. So if I know that it's 24 hours per cycle, if I flip that upside down, I get cycles per time, 1/24th of a cycle per hour, as opposed to 24 hours per cycle. So those two ideas are connected, and sometimes I'll mistake one for the other while I'm talking because I'm brain dead, and that's why. They are connected. If you change one, you automatically change the other. Because this is math class and we're typically going to be looking at our functions disconnected from reality, it's the period that's more important for you guys. But on the off chance there are a couple of future engineers in here, you do need to know that. Are you poking at a future engineer? Yeah. They will make you take physics in college, and you will see that at some point when you talk about waves in physics class. Good. Okay, we're going to look at our sine graph in a little bit more detail and just go over some basic vocab that we use to describe periodic functions. To help me, I need you guys to grab your unit circles. If you do not already have them handy. Unit circles. We need unit circles. We should not be reading English books in math class. We should not be taking naps in math class. Why are you in a college math class if that's what you're going to do with it? Frowny face. This is an elective and you don't need to be here. All right, some of us move quickly. Jay, do you have your... Perfect. What is the value of sine of 0 degrees? Sine is y coordinate. Y coordinate is 0. 0, perfect. We know sine starts at 0. We saw that on our calculator. Perfect. Someone else with a unit circle. Juliet, what is the value of the y coordinate at pi over 6? One half. So pi over 6, which is halfway between these two, would be here. Very good. Julie, do you have your unit circle? We'll come back to Julie. Dayanara, do you have your unit circle? What is the y coordinate at pi over 3? Square root of 3 over 2. And I think if you do that on a calculator, square root of 3 divided by 2, it's like 0.86-ish. So not quite 1. Somewhere in here between 0.75 and 1. Good. Julie's still looking. Someone at the back table. Cecilia, do you have your unit circle? What is the y coordinate at pi over 2? One. Yeah. Sign is the y coordinate on the unit circle. Good. If you remember how we filled out that unit circle when we did it together in class, we know that the other 3 quadrants are reflections of the first quadrant. I know that those heights are going to repeat. In the second quadrant, the y coordinate starts up at 1 and then goes down. So I know this pattern is going to reverse itself. And I know at pi I should be back at 0 because that's exactly across from 0. And then starting at pi, it repeats that pattern, but now the numbers are negative. So it's repeating this pattern, but downward. So 1/2, 0.86-ish, 1, 0.86-ish, 1/2, 0. And my hope is that those series of dots look familiar from Math 3. At some point in Math 3, they made you construct this graph. I see some nodding, which is good. I know, it was trauma. And you survived. Good job. It should also look familiar because we just built this on our calculator during our bell ringer. Nice, pretty smooth curve. As we go to the right, what's going to happen with the graph? It's going to repeat. So we go to the left, what's going to happen with the graph? It's going to repeat. Repeats forever because this is coming from loops on the unit circle, which can repeat in both directions forever. So we get a graph that goes forever in both directions. What's the domain? Infinity, negative infinity to infinity are all real numbers. Good. Good. Same for cosine, because we know cosine looks like this, but it's shifted a little bit sideways. Very good. We're going to label some terms that we use to describe periodic functions like our sine of x function. The first, I'm going to draw it, see if anybody remembers the vocab word. My 4th period came up with it before I even drew it. Cuts through the middle of the function. Midline, very good. This is our midline. Ooh, I don't want to write that there. Perfect. We have our midline. I have a point here. And at that point I just marked in blue, notice that the graph is increasing. And I want to mark the next point where the graph is at 0, but it is increasing. Here at 0, but decreasing. Here at 0 and increasing. So this is the end of my cycle. Same height, same behavior around it, increasing. This distance here, what do we call it? Amplitude's a vertical word, but we're going to get to that. Yeah, period. That's the one we just talked about. The length of a cycle. Single cycle, that's period. Good. Somebody said amplitude. The question is, where does that show up in our graph? So amplitude is the height from the midline of those peaks and those valleys, highest and lowest point. So I get the amplitude here at pi over 2 from midline to peak. This distance here from the midline down to the bottom of that valley is also my amplitude. We call amplitude A. So reminders. Period is one full cycle. So identify a point and the behavior around it. Here it's at 0, it's increasing. Find the next time it's at 0 and increasing. That distance is your period. How do I find frequency if I'm given the period? Frequency is what? 1 over means takes the fraction and flip it, right? 1 over, good. How do I find the amplitude? Very top, good. So midline to top. What we're going to do is we're going to do some examples together, and then I'm going to give you some time to work with your partners on your graphing calculator or on Desmos to graph some functions and identify period, amplitude, and frequency. Yeah? Okay. So on the backside, using what we know about periodic functions. So I know cosine of alpha equals beta. Somebody told me that. If I know cosine of alpha equals beta, what is cosine of alpha plus 2 pi? And I will remind you that cosine, we saw this on the front page, is a periodic function with a period of 2 pi. What happens to cosine if I go all the way around the circle? I end up back where I started. So what should that value be? If I take cosine and I loop all the way around the circle, I end up back where I started to begin with. Yeah, those two things should be equal. They're at the same point on the unit circle. So if cosine of alpha is beta, what is cosine of alpha plus 2 at pi? Beta. Yeah. Any whole number multiple of that period is a full circle around, will put you back to where you started. What about cosine alpha minus 6 pi? You should be asking yourself, is 6 pi a whole number multiple of 2 pi? Yes, it's 3 times 2 pi. So we went around the circle 3 times. We end up back where we started. The answer should be what? Beta. Very good. As long as it's a whole number multiple of the period, it's the same answer as where you started. We end up back where we started. 2 pi, 6 pi, 100 pi, anything that's a multiple of 2 pi. Good. Okay, we've got a little bit of class time left. I'm going to give you about 10 minutes. Do we have 10 minutes? Barely. What I'd like you to do is I would like you in your groups, grab Desmos or a graphing calculator, graph these functions, identify amplitude, period, frequency. I'm going to give you a hint for those of you using Desmos. On Desmos, there is a little wrench in the upper right-hand corner. If you click that and you go down to where it talks about the x-axis, you should see some information about the axis and then step, colon, and a blank. That's the setting for what the x-axis is counting by. You want it to count by pi. If you do that on Desmos, it's going to make it a lot easier to identify your period. You've got the rest of the period to work on this. I'm going to call on people for answers as our bell ringer on Thursday. If you have questions, let me know.